Here I'm going to talk about the fundamental theorem of arithmetic and explain exactly what it's saying. Now, the fundamental theorem of arithmetic is actually a fairly simple concept, but the notation looks absolutely horrible, and that makes it very intimidating looking. So let's demystify this a little bit, and then it'll make some sense to you. So let's go through what it says. It says, given any integer, n is greater than 1. So we're just saying any integer, 2, 3, 4, as long as it's a positive integer greater than 1, we don't want to use 1, because 1, what does it factor into? Just 1. Not interesting. So let's say we choose the number 12. I'm going to use this as a fairly simple example, and then we'll look at a more complicated one in a minute. So, for the number 12, there exists a positive integer k. So, there's some integer k. I don't know what it is yet. I don't know what it needs to do. I'm just going to say it's some positive integer. So it's 1, 2, 3, 4, somewhere down the line. Distinct prime numbers, p sub 1, comma, p sub 2, comma, p sub 3, comma, dot, 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 comma, p sub k. All right, so we're looking at these. Now, these are all prime numbers. That's why we put p there for them. So that kind of reminds you that they're prime. So they could be 2 or 3, 5, 7. Can't be 9 because 9 isn't prime. So it can be any kind of prime number, and there are k of them. And so instead of saying P, Q, R, we don't know how many there are going to be. We might run out of alphabet. What if it's a huge problem? Probably not going to happen with 12, but, we don't want to limit ourselves as to how many variables there could be. So we're just going to call them all P because they're all prime numbers, and then there are k of them, and that's where we get this k up here. So now that part's kind of come together a little bit. There's a certain number of prime numbers. That's all this part is saying. We have some prime numbers. There is a specific number of them for any particular integer n. And we also have positive integers, e sub 1, e sub 2, e sub 3, all the way up to e sub k. All right? So now these are another bunch of positive integers, and again, I have exactly k of them. Now, let's look at a little difference here. This said distinct prime numbers, p sub 1, p sub 2, all the way up through p sub k. Those all have to be different numbers. These do not. These could be all the same number. Such that, and then we have this big relationship. And this says that n is equal to p sub 1, so my first prime number, whatever it happens to be, maybe it's 2, maybe it's 3, who knows, to a certain power, e sub 1. So if I have a 2 here, it's to some power, maybe it's to the 5 power, we don't know yet. Times another prime number. This prime number is different from this prime number. But could this exponent be equal to this exponent? Sure. This exponent could be 1 even. And we know that 1 is not a prime number, so our p's can't be 1, but the e numbers could be 1. So that could happen. Times another prime number different from either of these two to another integer power, which could be anything. 1, 2, 3 could be equal to this, or all three are equal. We don't know. Times, times, times. Let's just keep doing this until we get to the very last prime number and raise that to a power. And now this prime number is different from all the prime numbers in between, all the way down the road. Okay, so now what is this saying for the number 12? What this is telling me is that I can write 12 as one particular factorization involving prime numbers. Now, we know the number 12 can factor a number of different ways. We could say that 12 is 1 times 12, or 2 times 6, or 3 times 4. But in particular, we're looking for a factorization that involves prime numbers. So 1 times 12, not really helpful. 1's not prime, neither is 12, and that really didn't do anything for me because I could keep writing this forever, right? 1 times 1 times 1 times 1 times 12. So how did that do anything for me? It didn't. It's, I just have a string of 1s. So let's get rid of that. All right, lose that one. All right, then we have 2 times 6, and we also have 3 times 4. So 2 times 6, well, this has got some possibilities because 2 itself is prime. So I can circle that. And then the 6, I could factor further into 2 times 3. And what I see is that then 12 is equal to 2, let's erase this part down here. So we've got 2 times 2 times 3. Now, right now, I have 2 to the 1 times 2 to the 1 times 3 to the 1. This still doesn't match what I want because I want there to be prime number bases and exponents, but I want all the prime numbers to be different. So, obviously, you can just tweak this by making it 2 squared times 3. And it's 3 to the 1. Do you have to write the 1 in? No. Just if you are showing what's going on here, then what you could say is, all right, P sub 1 is equal to 2. And E sub 1 is equal to 2 also because we have 2 to the second power. P sub 2 is equal to 3. And E sub 2 is equal to 1 because we have 3 is the base, 1 is the exponent. So 3 to the 1 power. So this gives you the breakdown for our fundamental theorem of arithmetic. Now we did this with starting with 2 times 6. Now what this fundamental theorem of arithmetic says is it doesn't matter how I started. What if I didn't start that way? What if I started with 3 times 4? I'll do that over here on the side. Then I have 3, which is a prime number, and 4, which factors into 2 times 2. So now what do I have? 2 squared times 3. I like to put them in order from small to large. Do you have to do that according to the fundamental theorem of arithmetic? No, you do not. It doesn't say that the P1 through PK are in order. It's nice to do that because then we all get exactly the same order. But they did allow for that, right? They said there's only one way to do this. Any other expression for n as a product of prime numbers is identical to this. Identical, exactly the same, except perhaps for the order in which the factors are written. So, you want to write 3 times 2 squared? Go right ahead. Totally fine. You still have the same thing as anyone else who did this problem, except for, perhaps, the order in which the factors are written. So now let's apply this in actually factoring and writing a number as a product of prime factors. So in this example, we want to write the number 235,224 as the product of prime factors. So what I'll do to get started is, my goodness, this is going to take a little while. So 235,224. You probably want to have a calculator with you right now. Now, what I can do is I can use my divisibility rules to help me move along a little faster on this. So I'm going to start with seeing if 4 goes into this number. And I can check to see if 4 goes into a number by looking at the last 2 digits and seeing if 4 goes into those 2 digits. And if it does, then 4 goes into the number. So we can see 4 goes into 235,224 because it goes into 24. So I'm going to go 4 times what? And let's divide. And I wish I had done this ahead of time. Let's see, we've got 20, and then that's 35, which is 8, and that's another 8, and then a 0 and a 6. Okay. So we've got 4 times 58,806. Now, I see that I still have an even number, so I can factor this further. I can make this into 2 times, and let's see, that would be 29403. Okay. Now, I don't have any more evens, and the 4 can factor into 2 times 2. So every time I get a prime, I like to circle it, because that's what they taught me when I was in school. So I just go along with it. Sure. All right, now I'm going to look to see 29,403. All right, well, we've shrunk this down quite a bit already. Is it divisible by 3? And I can tell that my divisibility rule for 3, I just take the digits 2 plus 9 plus 4 plus 0 plus 3, and I see, is this equal to a multiple of 3? Well, we get 11, 15, 18. And if you say, oh, I don't remember, I can even say, well, what's 1 plus 8? And that's 9. So I can keep adding digits together. I don't have to just add our original digits once and stop. So we get 9, which is divisible by 3, and in fact it's divisible by 9. So there's a divisibility rule for 9, so I'm just going to go ahead and make this a 9. And say 9 goes into 29,403. How many times? Let's see. That would be a 2, and that is 60, and that's 6, and 7. Okay, so I have 9 times 3,267, and the 9 is 3 times 3. There we go. That was easier. All right, and how about 3,267? Is that divisible by 3? 3 and 2 make 5, 6 makes 11, and 7 makes 18. Okay, so we can divide out another 3. Oh, we could divide out another 9. Let's do that. All right. So 9 into 32 goes 3 times, and that is 6 and 3. Okay. And so the 9 is 3 times 3. And 363, well, that one's pretty easy to see. That's divisible by 3, and I get 121. And 121 is 11 times 11. So now I've factored it as much as possible. So how is this the product of prime factors? I would say, how many 2's do I have? 1, 2, 3. So I have 2 to the 3rd power times, and then I have 3's. And I have 3 to the 5 power, 1, 2, 3, 4, 5. And then I have 2 11's. And there you go. So, is there any other way to write this as a product of prime factors? Well, I could write it like this. 3 to the 5 times 2 to the 3 times 11 squared. So I just changed the order. That's really the same thing. So other than changing the order, that's the only possibility, and that's my final answer for that.